Hey everyone, welcome back and let's write some more neat code today. I know I probably don't say this enough, but I just wanted you guys to know that I really love you. We're given a string s and we want to convert it into a palindrome by adding characters to the front of it. And we want to return the shortest possible palindrome that we can get. So considering the first example, the simplest thing would be if we had an extra a over here, then the input string itself would be a palindrome, in which case we just return the input string itself. We're not returning the length, we're returning the string that we can form. That a does not exist, so we have to add it ourselves. And once we do add that a, well, this is the shortest palindrome that we can form. So just kind of analyzing the problem, what would even be a brute force solution? Well, given the fact that this is the shortest palindrome we can form, remember what a palindrome is. With 2 pointers, we can basically say that these two are the same and check them off, shift the pointers inward. These two are the same thing, just keep going. By that definition, if this is the smallest string that we could add to the beginning of this input string such that the whole thing is a palindrome, that basically means that first of all, this prefix, what I'm going to call it, this is of length 1, so it matches the suffix, the string starting from the end, of also length 1. And if those match, then the subproblem becomes the inner string. And if this was the shortest string that we added, therefore the inner string was already a palindrome. So, in other words, another way to think about this problem is find the longest string starting from the beginning of the original string that is a palindrome, and this is the longest one. So once we identify this is the longest prefix of the original string that is a palindrome, then we say that all we need to do to make the entire thing a palindrome is just take this ending. We did not have a matching portion for the ending of the string, for the suffix of the string. So we take that portion and we create a copy of it and we append it, well, prepend it, I guess, to the beginning of the string. And that's the palindrome. So this is a little bit clever, but honestly, I don't think this itself qualifies as a hard problem, like this solution itself. This is more of a medium. The main thing of identifying this solution was just taking this problem and realizing that this problem is actually more simple than they describe. What we're really just looking for is the longest palindromic prefix of the input string. Now, how do you find that? Well, the brute force would be start at the beginning. Is this a palindrome? Well, actually, I guess a better thing would be to start at the end of the original string and say, okay, well, I want to know if from here to the beginning, is this a palindrome? How would we do it? Well, a linear time algorithm, possibly a 2-pointer approach. That's one way to do it. And if we find that this is a palindrome, okay, great, we're done. Now, if it's not a palindrome, well, let's try the second largest string, the second largest one ending here. So starting from the beginning, is this a palindrome? Well, yes, this time it actually is. So what do? Well, this was the index, let's call it the right pointer, where we found the palindrome that ends here, the longest one. So we take every character after that, create a copy of that string, add it to the beginning. And not just that, we would actually have to reverse it as well. Let me just kind of create a quick example to show you that. For example, this input string, 3x's. So this is where the longest palindrome will end starting from the beginning. So what do? Well, we take the remaining characters to the right of it. Don't just copy them to the beginning. That wouldn't result in a palindrome. Take the copy and reverse it and then add it to the beginning. So we get BA. That results in a palindrome. And that's more or less it for this problem. Now you can kind of see that in the worst case, if we're going to check every single ending position, that's O of n. And to check each ending position, we need to check if that prefix is a palindrome. That's O of n. That's n squared. And I mean, theoretically, to create the output, we kind of are going to have to create a temporary string. So I guess even that could be considered O of n space. But anyways, this is a simple solution. Let's code it up. So first, I'm just going to very quickly have a function that determines if a string is a palindrome between 2 pointers. This is the easy part, so I'll try to keep it short. Before the pointers cross each other, if the characters aren't equal, return false, it's not a palindrome. Otherwise, we get to the end, return true. Don't forget to update the pointers as we go. Left will be incremented, right will be decremented. Now down here, nothing crazy for right in range, length of s, but remember, I kind of want to start from the end, so I'm going to actually reverse this range. You can learn this in the Python for Coding Interviews course if you're not familiar with the syntax. It's on Leetcode.io, but now what do we want to do? We want to know if the string ending at index r is a palindrome. Well, we have a function for that. Is pally, given the string s, starting from the beginning, index 0, and going up until index right. If it's a palindrome, this is the longest one that we found. It's the longest one that exists, so we want to return. Now, if we never find a prefix that's a palindrome, that would actually only occur if the input string is empty, which I guess actually is a test case. That's kind of annoying, but whatever. Down here, let's just return an empty string, because I guess technically an empty string is a palindrome. But anyways, here, what do we want to return? Well, we want to take the original string s, and to it, we want to add the reversed suffix. So that's what I'll call it here. The suffix is going to be the string starting, I'm going to slice it. You can also learn this in the Python for Coding Interviews course, from right plus 1. So right after that index, and we're going to go up until the end of that string, and then I want to take this and reverse it. The easiest way to do that is here I could do : -1. I guess I'll just do that down here just to make it technically correct, because this is the suffix, and then that suffix we are going to reverse it in line and then add that to the string. So that's the whole code. N squared. Oh, that's funny. This time it actually gives me time limit exceeded, but I promise you this solution actually did work earlier. Here, you can see I had pretty much the same solution and actually did pass. So anyways, but that's okay because we're not done yet. I know you want to see the optimal solution, and that's what I'm going to show you. So there's actually several solutions that could be solved in linear time for this problem. KMP does come to mind, and honestly, that's the one I was going to do for this problem. I recorded it, I looked back at it, and I realized that actually my explanation was more complicated than one I've already done in the past. So honestly, if you want to learn the KMP algorithm, I do have a video for it. You can just search for it on YouTube. I will tell you though, it is a 35-minute video. And if you're thinking, damn, 35 minutes to understand this really hard algorithm, no, don't jump the gun. Honestly, I don't think you're going to be able to understand it in 35 minutes. It's an extremely complicated algorithm. Even people who think they understand it, I'm not convinced. I'm pretty sure most people just memorize this algorithm. And I think the people who think they understand it are just fooling themselves. They're just lying to themselves. It's not something you understand very easily. The intuition is insane. I'll be showing you the Rabin Karp algorithm. I'm not sure if I'm pronouncing that correctly. I think conceptually it's a more simple algorithm, so let's do that one. Thankfully, there is an alternative. This is how it's spelled. I don't know if I'm pronouncing it correctly, but it's basically a hash algorithm. It's conceptually very, very simple. The idea is this. I have my input string here. I take the reverse of that string and I have it here. So just so you realize, I literally reversed the string. So this is the string now. Like, just take every character, put it in the opposite spot. I know they look very similar, but no, it's technically reversed. This one started with 2 A's, ended with 3 A's. This one has 2 A's here and 3 A's here. Okay, so now you believe me. Imagine I had an algorithm, a string comparison algorithm. Let's not even get into hashing just yet. Imagine like I'm counting prefixes from this string and I'm counting suffixes from here. So I check these two, they match. I check these two, they match. I check these two strings, they match. Now, eventually we'll get to this spot and we'll get to this spot and we'll find that this was the largest prefix that matched the suffix of the reversed string. What does that tell us? That tells us this is a palindrome. Why is that the case? Because if you take a string, let's say ABA, and you reverse it, it's still ABA, that must mean it's a palindrome. Reversing a string is another way of determining that it's a palindrome. You don't necessarily need the two-pointer approach. That's going to be very relevant here. That's why we know it's a palindrome, because it matches the suffix. And remember, this entire thing was reversing the input, and all these characters ended up in this position. So if this matches that in the reverse order, it's a palindrome. So now you believe me that by matching this with this, we can determine if this is a palindrome. Okay, but the way I've talked about this, it's still going to be an n-squared algorithm, because comparing a string of size n with a string of size n, first of all, we're going to have to slice it. That's going to be a linear time operation. And then the comparison is going to be a linear time operation. And we're going to continuously do this. It's going to end up n-squared. Well, the trick here is that actually a string can be converted into an integer. And now that's what I'm going to be talking about, the hash part. You guys see this number over here, right? This is a base 10 number. And you could have a number like this. It's a base 2 number. Base 10 means that this spot is the ones place, right? In other words, it's counting 10 to the power of 0, which is 1. This is the tens place, 10 to the power of 1, which is 10. This is the hundreds place, 10 to the power of 2, which is 100. What we want to do is take this, and you could call it encoding or serializing this. I think encoding might be the better term, but I don't really know. But we want to basically convert it into an integer. Given the fact that the input string is going to be lowercase a through z, at the very least, what we want to do is have a system where each character will be mapped to a specific spot, and like that should not overlap with this one. These two numbers, they should be independent of each other. And if we want that to be the case, we at the very least need a base 26 system. At the minimum, we need base 26. Now, generally, this algorithm is actually implemented with a larger base, because with this algorithm, there actually can be collisions. We'll talk a little bit about that later on. But actually, if you do base 26, it will pass on Leetcode, though I think we'll do base 29, I guess, because it's a little bit bigger, and also because it's a prime number that will help reduce collisions. But I wouldn't get too much into the weeds of this stuff. It's very mathematical. Anyway, so now what we want to do is first, let's just focus on the prefix aspect of it. Let's encode this into a base 26 integer. Because if we can do that, and if we can also take the suffix and encode that into a base 26 integer, then the comparison between integers is generally much more efficient than string comparison. So that'll be constant time. That's the motivation behind this algorithm. So conceptually, very simple. If you try to read the Leetcode editorial, though, they don't, for some reason, ever explain the intuition. So that's probably why you're watching this video. Now, given that our number initially starts as 0, the mapping that we use, lowercase a, usually we'd map that to 0, and then lowercase z would be mapped to 25, and then, everything in between. But given that our number starts as 0, how do we distinguish between an initial 0 and an a? Well, for that reason, we're going to actually start our mapping at 1. So a will be mapped to 1, z will be mapped to 26. Relatively easy to create that mapping. I'll show you in the code. Assume we have that mapping. What do we want to do? Well, in this example, it's 1, so we want to set it to 1 now. Just add 1 here. Okay, so we get the 1 there. Now we have a over here. So what do we want to do? Well, we want this in terms of like the integer to look like this, 1, 1. But remember, this is not binary, nor is it base 10. This is base 29. So what this itself represents is the fact that we have 129 and we have a single 1. So the way to do this would be to take everything we have, shift it to the right. But remember, this is not binary. We can't actually do bitwise shifting. So how do you actually shift that to the right? Well, you know how in base 10, if we want to shift this to the right by 1, we just multiply it by 10. The same thing down here. Multiply it by 29. So now it will look like this, 1, 0, and then we'll take the 1 here and then add it there. And I'm just going to continue one more time. So once again, we're going to shift this to the right and we'll get 1, 1, 0. We'll take this, it maps to a 3, add that there. So now this is what we have. We started with a 1, then we had 1, 1, and now we have 1, 1, 3. Now we want to kind of do the same thing with the reverse, because we want to recognize that this prefix matches this prefix, and we want to eventually recognize that this prefix matches this suffix. Sorry, I said prefix a second ago. How can we do that? Well, it's actually not that complicated. The reason for this one, we're shifting everything to the left, is because like here we have 1, 1, 3, and now we want to add this to it. I think that's going to be 5. So we have to shift it to the left to make room. Here, we're going to kind of do the opposite. Okay, we have a 1 here. Great. Now we have A, it's a 1. So instead of shifting everything we have to the left by 1, just take this guy. It represents 1. So shift it to the left, or in other words, multiply it by 29. Great. So now we have a 1 here. Now C, let's say that's a 3. We want it to go in the third spot. The ordering does matter, because that's how we know that this is the same as this. So basically what we do is we take that 3. If we were to multiply it by 29, that would give us this spot. This time we actually want to multiply it by 29 squared, because remember, this spot represents 29 to the power of 0. This spot represents 29 to the power of 1. This spot represents 29 to the power of 2. The easiest way to actually do this would probably be just to keep track of that, I guess, which I'll call the power. We could technically use the index I that we're going to be using like as the iterator, because this is index 0, this is index 1, this is index 2. We could technically do that, 29 to the power of I, but it's probably easier just to start out with 1 and then take that and multiply it by 29 each time, which will give us something like this. And then here we'll get 29 to the power of 3, etc., etc. Hopefully you have a little bit of the intuition of the math now. Almost done. Sorry, I'm just a little tired if I sound annoyed. Here, of course, we would have seen that these two match, but clearly this does not match that. So this is not a palindrome, but we're going to keep going. We're going to see this is a 5, this is a 5. These don't look the same to me. We're going to see that this is a 3, this is a 3. Once again, this is not the same, but we get a 1 here and we get a 1 here. These are not the same numbers, but I add one more 1 here. I add one more 1 here. Now I see this number is the same as this one. So this is the longest palindrome we've seen so far. Make sure to remember the index that it ended at, similar to the previous solution, because once we're done, we're going to take everything to the right. This is the suffix. We're going to reverse that, and we're going to add a copy of it to the beginning, and then we're going to say this is our result. So hopefully conceptually this algorithm makes sense to you now. It's much more simple than KMP, but if you enjoy suffering, I mean, I do recommend you go watch that video too, but I'm going to try to keep it simple for today. Okay, so I'm going to now start with a couple variables. One is the prefix hash, like the integer that represents the prefix string, and we're going to have a suffix for the same reason. We're going to be doing this base 29, though you could use a different number and it'll probably still work. And I'm going to record the last index. Let's just call it that, last index. And I could set it to 0 initially, but remember the way we're going to implement the code. We're going to get the suffix, assuming that it ends at the last index. So we'll start at last index plus 1, and we're going until the end of the string. So that's the suffix, so that'll actually be this. And then we're going to return s plus the reverse of the suffix, so like that. The problem with this approach is if the input string is empty, I think we're probably going to have issues with this. I'm actually not 100% sure, so maybe we'll just run it and we'll see, but I'll leave a comment here. I think this should be starting at -1, because I think we'll get an index out of bounds error here, or maybe not. Anyways, now we want to go through the input string. I'm going to use enumerate in Python. It's pretty nice. Gives us the index and the character at the same time. And then I want to create that mapping, which I told you is pretty easy, and I did not lie. We can just take the ASCII value of the character, subtract from it the ASCII value of lowercase a. Now this would create a mapping where a would map to 0 and z would map to 25, but we want to just add 1 to that mapping. So just offset it by 1. Remember, for the prefix, we just want to add to it the current character. But before we do that, we potentially want to shift the prefix to the left by 1. We can do that by multiplying it by 29. So let's do that. Prefix multiplied by the base. Initially, the prefix is 0, so multiplying it by the base isn't going to do anything, so that's why this works out. And we're going to do something similar down here for the suffix. Suffix is going to be added with the current character multiplied by 29. But this is a bit misleading because the first time it'll just be multiplied by 1, the next time it'll be multiplied by 29, the next time it'll be multiplied by 29 squared. So what we can do is something like this, call it the power, initially it's 1, multiply it by the power, and then for the next iteration of the loop, just update the power by multiplying it by the base. Great. And then at the end, if the prefix is equal to the suffix, well, not at the end, at every iteration of the loop, we will check that so that we can record the last index. So at this point, we'll say the last index was I. So great, we're almost done, I promise. The only thing is that by doing it this way with a relatively large string, this number in some languages could overflow. So to handle that, we can mod it by a really large prime number, which is smaller than base 32. And one common number people use is 10 to the power of 9 plus 7. So this is basically 1,000,000,007. It's a prime number and it's smaller than a 32-bit integer. So to make sure that we don't ever overflow anywhere, here I'm going to mod it by the mod. Here I'm going to mod that by the mod. That's why I put parentheses around everything I was anticipating. And mod this, and then down here mod this guy as well. Now, theoretically, there could be a collision given the fact that eventually we are going to mod this. Like for small input strings, there probably wouldn't be a collision. But given the fact that we're modding this, we could end up with two different numbers, two different prefixes and suffixes. And then at some point after we mod it, we end up eventually having the same prefix and suffix, like it was the same remainder, but the original values were not necessarily the same. So that would give us a false positive. We'd see that we found a matching prefix and suffix when maybe it doesn't actually exist, and we would erroneously set this to I. Now, one potential fix for that is to verify here, because theoretically this should not occur very often. In that case, here we could verify that the original string, like the actual prefix, not the hash, but the actual prefix matches the actual suffix, but that is obviously a linear time operation. So if this were to execute every single time, potentially in the worst case, for a string that just has like the same character in every spot, that would not be very efficient. So for that reason, I'm not going to put it there, but that would technically make the solution more correct, but less efficient. So let me run this now. You can see it works. It's pretty efficient. I hope you guys believe me now when I say that I make these videos for fun, because if you just go through the list of videos I have, you can see that if I really wanted views, if all I cared about was money and subscribers and views, I'd just make these random reaction videos, which get like 100,000 views, whereas the Leetcode videos get a few thousand views. But you guys know that I actually genuinely enjoy doing this stuff. So if you also enjoy it, feel free to like, subscribe, and maybe check out Leetcode.io.